All right, guys, we're going to get started. 6 o'clock. Thanks, everyone, for coming. This is the Cleveland AI Group, as you know. Billy's going to be speaking, and then Bobby over there is going to be speaking as well. And if Ari shows up, he will be here.
Sorry, I cut it.
Oh, man. Sorry.
It's all good.
I didn't recognize you. Okay. Yeah, that's good. All right. Okay, well, then we're all here, so we're ready to go. Just a reminder, I guess, of a few things. We are, so I mean, the mission I've read before, it's on our previous videos, but I guess I'll just quickly go through it. We're here to educate mostly and kind of bring the technology of AI into the public domain a little bit. It hasn't really gotten into Cleveland too much. It's still early days, and we'd like to help accelerate that. Primarily just like helping people bring this into industry and so they can use it, and I mean in the personal projects in their lives. That's the goal, and hasn't changed. We so far have only been doing talks. We're going to be in a few different events coming up in the next couple of months. I think next month we're going to be doing a showcase where anyone who wants to can just come in and talk for a little bit about the projects they're working on. So, like, just be 5, 10, 15 minutes, whatever you got, you can just put off, and we'll just have a lot of people rotating, hopefully, and we'll all be showing off what we're working on, and hopefully it'll create some good collaboration between people and good conversations. And then in April, we'll be having another regular event like this or something similar, but we'll also be having like a special event on AlphaGo where we'll be showing the AlphaGo documentary. It's great. I think of it as like one of the greatest achievements of like recent AI, and then we'll be talking about like how it works and going into like the details of the papers that they've released and stuff. So that should be cool. That'll be downtown at the Health Center, the Global Health Center for Innovation. So other than that, there are a few other meetups coming up. I think there's an R user group meeting. There's always a Python one. Big data meetup is probably in March, and so yeah, we'll. I hope you guys check those out because those are all really good groups, and yeah, and they've supported this group too, and we all kind of are trying to do the same thing. So yeah, for that, I think I'm gonna bring Billy up here and share the screen, and he can get started. So he'll introduce himself, but Billy's been here before, and he gives great thoughts, and I'm excited to hear him speak. So, thanks.
Thanks, everybody. Let's keep it going a little bit for Jason for getting this together for another month. So, like you said, I'm Billy. I'm a student here at Caig. I do research in artificial intelligence, in particular, online learning and tuning hyperparameters. If that doesn't mean anything to you, that's okay, because that's not what I'm here to talk about tonight. Tonight, actually, I'll be talking about batch learning, specifically the perceptron. So the goal for my talk tonight, this is a very beginner-geared talk, is to kind of take you from just a little bit of knowledge of coding and a little bit of math up through your first supervised learning algorithm. Kind of demystify like how that works and what's actually going on there when people talk about things like training and testing and the decision boundary, things like that. So to get started, let's overview where things are going. So like I said, gonna be going through the basics. This will be very hands-on. So we'll start with a problem, and then we're just gonna walk through the problem. First thing we need is machine learning, so data. And then after that, we'll look at how we can solve it by ourselves, right? Like how you and I would solve it, the process we go through. And then we'll step back and try to formalize that process into code. And then finally, we'll talk a little bit about some of the pros and cons of the perceptron in particular. And then finally, I'll just give a little bit about neural networks at the end, just to kind of motivate that. But that's definitely not the focus for today. Before we get going, toolbox for the talk tonight, it's done in Python. In fact, this presentation is a Jupyter notebook. So that'll be up on the Meetup's GitHub afterward for you to pull down. I'd encourage you to. You could play around with the code, run it. If you find any bugs, you could even submit a pull request, I guess. So yeah, and then in addition to Python, just a couple typical libraries you'll see used with machine learning. NumPy, which just allows us to do vector and matrix math. Don't worry, it's nothing scary tonight. And then a plotting library for making pretty pictures. So like I said, we need a problem. And this was the hardest part of coming up with the talk for me. I wanted it to be something interesting, but at the same time kind of simple enough for us to approach. I'd kind of given up on this one night and was browsing around YouTube and Reddit and stuff. And it kind of hit me, right? There's this huge problem in society, and I don't know if it's come across any of your feeds at all recently, but it turns out people are having a really, really hard time telling the difference between Tide Pods and candy. And it's really a topic that it doesn't seem like it should be that hard to do. So I thought it'd be the perfect thing. What if we trained a machine learning classifier, a perceptron, that could tell the difference between a bag full of laundry detergent and a gummy shark? So like I said, first thing we need is data. So I went out and I bought a bunch of candy, a bunch of laundry detergent pods, and I took 2 measurements. One being the transparency. So I just showed a light through it and then measured the percentage of light that came out the other side. Second measurement was the weight in grams. And then you'll see the third column up there. I recorded it all into these CSVs, is a label. So machine learning is in math and numbers. So we're going to translate the labels to numbers, right? So 1 for candy, and then we'll do -1 for Tide Pod, right? -1, bad, you can't eat it. Well, you're not supposed to eat it, but yeah. And then in addition to the training set, right, I have a separate file with 20 other data points in there. And this is my test file, right? Can anybody spot the difference between these two? Feel free to yell it out. What?
Less instances.
Less instances. And also this one's missing the labels, right? And this actually kind of arises a subtle point that I just want to touch on, right? If you remember, the goal of machine learning is to build things that generalize. So we want to make sure that they're working on things that they haven't seen before, right? Finding the patterns and taking advantage of those patterns to do the task. So you'll imagine, like if I trained something, right? If I was trying to teach somebody and I gave it all those labels to start with, and then let's say I ask it the first thing in the row. So I have an object, transparency 83.7, weight 16.6. What is it? And then it just spits out 1. Well, that's easy. It could have just memorized that, right? It's like giving a test in high school where the teacher gave you all the questions beforehand, and you just had to memorize the multiple choice answers, and you didn't actually learn anything from it. Same sort of concept here. So we have the test file, and that doesn't have any labels on it. So now we're going to be able to see if the algorithm, when we test it, actually kind of learn the patterns that are underlying things and isn't just memorizing and regurgitating information to us. You'll see I do have the labels in a separate file here, and that's to check our work. You could put them in the same file and hide them from the algorithm, but for the sake of example tonight and just to illustrate it easier, they're in a separate file. So there's our data. Take a look at it here. Since it's in 2 dimensions, right, we could plot it, take a look at it. You'll see the candies in blue and the Tide Pods are up there in red. This is important as well. You want to kind of see what you're up against. This looks actually pretty nice, pretty friendly. It seems like we could draw a line in the middle there. It's always the case that we could look at the data. So we could also do things like look at individual statistics on the column. What's their range in values? What's the median, the mode, standard deviation, things like that. And then we'll go ahead and superimpose the test instances on there, and we'll put those in black. And now our job is to guess the color of what those black dots should be. Right? Are each of those a piece of candy or a bag of laundry detergent? Yeah, if you're having trouble seeing back there, go for it. So this is the part where you guys are going to help me out. In particular, if you don't exactly know where I'm going with this yet, how would you tell the difference, or how would you determine whether or not one of those black points should be red or blue? Proximity to the color? Do you have any other ideas?
Political affiliation.
Absolutely. So we could do proximity to the other colors, and that's an algorithm called nearest neighbors, I think. So you could look that up. But actually tonight, for the sake of the example, what I want to do, or how I want to look at this, is what if we drew a line straight between those there, right? Straight between the blue and the red in our training instances. And now we have that line, and we can say, okay, if it's above the line, right, probably a Tide Pod. If it's below the line, probably a piece of candy. So let's do that. A little bit of algebra first. You all remember the equation for the standard form of a line, ax plus by equals c. We're going to do just a little bit of manipulation on that to make it nicer to play with. So we'll subtract c from both sides and call negative cd, just for naming. And then instead of x, y, z, and a, b, whatever, we're going to use x1, x2, x3, just so we don't run out of letters. And then instead of those constants, we'll call them w. So w1, w2 for weights. And then that first term there is the tricky part, right? So instead of having d, I replaced that with w0 times x0. And w0 and d are equivalent, right? It's just a different letter for the same thing. And then x1 is just always going to be fixed to the number 1. And if you don't x0 will always be fixed to 1. And if you don't understand exactly why I did that, it'll become evident later. But just understand that that top equation and the bottom one are mathematically equivalent. So now that we have it, we'll plot a few lines. So we'll try with weights of 0, 1, and -1. And that's already starting to look pretty good. We could play around with it a little bit more. I spent some time doing this. And if you're really interested, like I said, you could pull the notebook. But then I came up with this one, which seemed to fit it pretty well, right? So then I could superimpose the test images on there again. And I kind of have my classifier in a way. So here's the code that goes along with making these classifications. And again, it's handpicked because we're the ones setting the weights. So then I could just do the classify, call that classify function on all of my test instances, get a prediction, and just like that, I'm done. That wasn't all that hard, right? There's a couple problems. For starts, what if I'm not very good at drawing lines? Right? What if I can't guess the magic points? That's not very, this wouldn't work out for me. And then second, this gets a lot harder as we add more features, right? So if I added more columns to that CSV, like if I want to take the width and the length of those, now all of a sudden I have 4 things, and at least I have trouble visualizing 4 dimensions. I don't know about you. So this isn't going to generalize as nicely as we like. So what we'll do now is we'll step back and we'll kind of try to figure out what we were doing there in our heads and come up with the instructions for the computer to do it. Come up with the code that corresponds to that. Before we do that, a couple housekeeping things. One is vectors. Kind of talked about them a little bit at the beginning. So if you don't do math, you're not that into numbers, all a vector is like math people have a fancy word for like a list of numbers. That's all it is. So you can see my weights, instead of being like W0, W1, these separate numbers, they're a vector, right? And if I wanted to add more weights, I just make the list longer. Same with the features, right? So I had features x0, x1, x2. I just put those in a vector. And then actually, I got to give the math people credit on this. There's a thing called the dot product, which means I take each pair of numbers in the vector, multiply them together, and then add them up. And that's exactly how we were making the classification right there, right? So now instead of walking through that complicated explanation, right, we could just say we take the dot product of the weights and the vectors, and then take the sign of that, right? One for positive, -1 for negative. So that's vectors. Second housekeeping thing, if you haven't seen this before, oh man, it's not there. Jason, where's your terminal? I can just do this here.
Yeah, you should be good. You might not.
Yeah.
Just going to go into the.
Yeah, I'll just show this graphic here. There's the picture I was looking for. So that's what a perceptron looks like. And this is kind of the visualization that at least I see used a lot. So again, you have your feature vectors over here, and then your weights. Each of these get multiplied together, summed up, and then it goes into the circle. And we apply a little function there. So we use the sine function in this case. And then we spit back out a value. Right? So this is the general picture. And at least I find it kind of useful when I'm thinking about these things. Hopping back to the presentation now, the algorithm, right? So we're going to formalize that process we did before, where we drew the line, and then we saw how we did, and then we updated, and then we'll just repeat that again and again until it gets good enough, because computers are really good at doing things a lot of times in a row. So first step, classify, right? Couple differences here from before. I'm making use of that dot product that we talked about. That comes from that NumPy package that we did initially. And then you'll see I changed the classification function, or the function that sat in that circle. So we're no longer taking the sign. We're doing something called like clamping the value down. What that means is if I'm bigger than 1, I'm just going to call it 1. If I'm smaller than 1, I'll call it -1. And anything in the middle, I leave it as it is. And this like lets me do something kind of nice that wasn't happening with the sign value before, right? In the now that number that comes out of my perceptron kind of gives me a confidence in a way. So if I get something that says -1, right, it means it's really far away from that line, which in turn we can kind of interpret as the classifier saying, yeah, I'm really sure that this is a Tide Pod. Don't eat it. On the flip side, 0.5 is saying, you know, I'm not so sure, right? If I had to guess, I would say it's a piece of candy, but like you might want to have poison control on speed dial just in case. And if it's coming up even smaller than that, right, like -0.02, that's saying, yeah, too close to the line to really make a call. I flipped a coin and it came up tails, so I'm going to say Tide Pod, but really I'm not that confident on that prediction. So that kind of covers the classify step for us. Not too much new there. Next is the loss. And what do I mean by loss? You can think of it kind of as distance from the line. So, or in other words, am I right, am I wrong? Do you remember the blue points are supposed to be below the line, right? And this one's above the line. So it's being, the classifier is guessing that it should be -1, and its real label is 1. So I can take the difference between the two of those. I said that backwards. So I'll take the true label of the instance 1 and subtract it from the predicted label, -1. So there I have a loss of 2. And you can play around with different functions for loss there. And now, this is the hard part. This is the last one, update. So the real reason behind like how we do the step, how we do the update, is it's a procedure called gradient descent, which gets involved in like a little bit of calculus, and we could talk about that, almost give that its own talk. So what I'm going to try to do is just motivate why we're updating how we do, and then I'll step back and kind of explain the math just a little bit. So again, remember on that last slide, we had the loss. So we want that point to be beneath the line, actually. So the logical thing to do, right, is to actually push the line a little bit toward that point when we got it wrong, right? So you remember the loss on that was 2. So I can take my weights here, and if I multiply that by the loss, which was 2, right, that's a positive term, so it's going to kind of push the weights up. And I know I'm doing a little bit of hand waving here. So then if I guess that a negative point, a red point, should be positive, then I push the line downward, closer to the red point. And it kind of works its way there. And what you see here, this term here, that's what's doing it. So the instance is kind of giving me the position above or below, times the loss is helping me shift it. And then that 0.002 is a step size, right? If I stepped all the way as far as the loss told me, I might kind of like overshoot some other points, and we'll look at that later. So I know I didn't do a great job explaining exactly how we got there, but as long as you understand that concept of what's going on, that's important. And just to motivate it, for those of you who are more curious, right? So this process called gradient descent. So you can think of us plotting our loss function, right? So I have like my weights. I plot the loss as a function of the weights, right? And this gives me this nice big kind of hilly map, if you will. So then all of a sudden my current loss is a point on that map. And I want to make that as small as possible, right? Ideally, I have 0 loss. And where's 0 loss? That's like downhill, all the way in a valley. So what we use a mathematical tool called the derivative, or actually, since we're in vector space, the gradient, which tells us which we can use to find which directions down the hill. And then we take that step size, that tiny little number, down the hill in that direction. And then we reevaluate and repeat. And eventually, if we keep moving downhill, we'll end up at the bottom of a valley. And that step size is important as well, because if that's too big, right? Imagine that I say, okay, like downhill's that direction. I could take too big of a step and actually overstep the whole valley. And if it's too small, then I'm moving too slow, and it's going to take me an awful long time to get to the bottom.
Is there any heuristics associated with calculating that step size?
Yeah, that's a great question. So one way of doing it, right, is you can test it out with a few different ones on that training data and then see which one gives you the best results on that. But there's also a lot of research that goes into that area, and there's ways to play with it adaptively too. So like if you're really far off, you're more comfortable taking a bigger step. You can see like which direction you've taken past steps in and kind of build some momentum, so to speak. So a lot of resources on there. But if you Google like tuning step size in gradient descent, you're going to get a ton of hits on that. Great question. Anyone else before we keep moving? All right. So we have a classifier set up, right? So now we can kind of train it. This is just kind of pulling that loss function that I had up there into that class. And then, right, so here it is after one iteration. We go through all the points, check the loss, update it based on the point. We got a little better than when we started, if you remember that plot. And then we could repeat it 3 times, 10 times. And then finally, after about 30 times, that more or less converged. So we've got it. We trained our first classifier. And now, what do we do next? Go for it.
So just because you know that the line does fit,
Mm-hmm.
you still don't know that that's the optimal line to use. Right?
Correct.
There's still no way to know whether a little bit higher or a little bit lower, wherever that is. You know, the slope might be good, but the height might not be.
Yeah, that's a really great observation.
So how do you know when you really hit the
Can-
bottom of that slope?
Yeah, can I ask you to wait on that one? I got some slides that have some pictures. Hopefully those pictures will show up. But yeah, great observation. Yeah, so this is just a formalization of what we had here. I kind of wrapped that loop I had in a train function. And I'm going to loop through the instances in a random order every time. And then I'll have a maximum number of iterations. So if we can't get to 0, then we'll go ahead and we'll stop training within those iterations. And we could use this then to train on the training points and then plot the test points on there as well. So that's kind of what it looks like there. And then we'll go ahead and use the classify function to spit back out the predictions. And we missed a few. What's going on here? So it fit the training points perfectly, right? Oops. But it's kind of missing on some of those other things. And I think this comes into kind of what you were talking about there. So that's not really the only line we can draw, right? In fact, there's a lot of different lines that could fit in there. And which one is the best? And the answer I'm going to give you is for the perceptron, it doesn't really care. It's just going to find one that kind of minimizes that term based on where it started, and then it's going to settle into there. Now, I do agree with you that playing with that intercept is going to make a difference, right? So in this case, maybe we'd want to push that line closer to, like pull this blue line, right? So it's really close to the candies because we'd rather somebody not eat a piece of candy than actually eat laundry detergent. And that kind of distance there is called the margin. And there's different classifiers that are based on like maximizing that margin to different extents. But the perceptron just kind of settles in there and finds one. Now to improve that though, what we could do is we could start it a few times with different weights, and then we could see which one performs best on our training set. And then choose that one to be the one that we deploy into the wild, you know, like give to our kids to use before they decide to eat a piece of candy. So yeah. And then what else do I got? Yeah, so that shows kind of how the differences are going.
You said you might choose the one to best on the training set, but with all the different lines, they're all 100% on the training set.
Correct. Yeah.
So there's not a best.
As far as the perceptron,
There's the best on the test set.
correct. Yeah, yeah. But I guess the best, when I say the best on the, could you repeat the question?
Sure. The first line you just correctly classified everybody as a training set.
Yeah.
You can't do better than that.
Correct. Yeah.
So no line would be best.
Mm-hmm. Right. Yeah. Yeah. But then I can evaluate the performance on the test set, and whichever one performs the best there, kind of choose that as my one to deploy.
Okay, so that's what
Yeah. Yeah. Sorry about that. Any other questions? So wrapping up then, just to review what we talked about, right? We started with the data. The part I want you to remember that is the difference between the training and the test set. That's a really, really important concept in things. And if you don't kind of follow that procedure, you're going to probably end up thinking you're doing a lot better than your classifier actually is. And we did the algorithm, that general kind of framework of classify, incur the loss, and update. And if you're interested in more about that, look up the procedure of gradient descent. And if you have 45 minutes, you'll have no problem understanding it. And then finally, we checked out the performance on the test set. And that's a really important step as well, right? Because your job as the machine learning engineer is to understand the results that you get and the limitations of what you do. So I don't remember if this question was asked, but what if I couldn't draw a nice line between my data, right? In this case, then the perceptron as I used it isn't going to work out for me. Right? If I want to classify something more complex, right, I'm going to need a more complex algorithm. So if I'm trying to fit something where the Tide Pods were clustered in the circle and the candies were around them, the perceptron's not going to give me great performance on there. I'm going to have to do anything else. So understanding the tools that you're using is really, really important. And then I promised a little bit on neural networks, deep learning. I wanted to feel kind of cool too. So let's see. That was our picture of the perceptron. Remember that? And then this is our picture of a neural network. So all it is a bunch of perceptrons kind of hooked together, right? So because these all output a value between -1 and 1. So then I could just take that value and a perceptron takes in, continuous numbers or even discrete numbers and just feed it to another perceptron. And I could repeat that as many times as I want for as many perceptrons as I want. And that's how you build a neural network. Couple points I want to bring here. Number one, when people talk about training a neural network, for those of you who aren't familiar, what that means is that means getting these weights set to the correct values to give you the output, right? So when that algorithm is kind of learning, so to speak, to tell what a picture of a cat is, it isn't getting this kind of like higher ordered like picture in its head so much like that you and I do. It's setting these weights the right value to output that. And I don't want to like kind of look down on it then from that sense, because it's really, really beautiful, like what you can accomplish just by scaling something so simple. And the results that people get doing that are incredible. So the one thing that changes though in the training process, right, is you'll remember we kind of looked at the output and then use that to update these weights. Well, it becomes a little trickier when you say, okay, what effect did this weight have on this final number? And there's a really beautiful algorithm called backpropagation that people use to do that training. And if you're into math or even just curious, I'd highly encourage you to look that up. It's a pretty neat thing. But again, it's just beautiful, like the kind of results that we can get from taking something simple and scaling it, right? So that same thing that we use to solve, the simple problem of telling the difference between like a Tide Pod and a piece of candy, we can scale up and use to solve more complex problems. Problems like telling the difference between fiberglass insulation and a piece of cotton candy. So that's all I have for tonight. I think we have maybe 5 minutes for questions, and I'll be around afterward too.
I get the feel that this is not a real life problem.
Not yet. It's coming though. They tell me.
It's toddlers that we're concerned about that are to differentiate the candy Tide Pods. But when you think about teenagers that are deliberately biting into the Tide Pods, you're going to help them find the Tide Pods.
I don't think we're going to help them with that one. I'm not sure I have a solution to that problem. Anybody else?
I got the solution.
All right.
Psychologists said kind of arguing that this generation is more on the discipline side. So this Tide Pod is kind of attacking out of that, but kind of like you're not going to stop me from hearing anything.
Poison will do its work, I'm sure.
Yeah, natural selection in a way. Go for it, Dave.
I have a question, Billy. Will you be posting your code online?
Yeah, it'll be up on the Meetups GitHub, so you can pull it down. So yeah, play around with it. Feel free to email me with any questions. Oh yeah, absolutely. Dave asked if the code would be available online. Anyone else? Go for it.
Just a comment, because continuing on my question before, if you choose the line to fit the training data, and then you look at the test data, you want to find something that fits the test data better, then you're in danger of overfitting.
Yes. Once again, yeah.
A bunch of models, and you indirectly trained on the test data as well.
Mm-hmm.
So a lot of people will hold out another test.
Yeah,
For
for
you've
validation.
done well on the training and the test, then you have the validation set, or whatever you give it. You test on that, and then you're done.
Yep, absolutely.
You have to have a line and you have curves.
So the perceptron's only going to draw a line because of that form we had there, right? Remember we started from the standard form for a line. And what happens a lot of times when you get into more complex things, right? It's nice to draw lines because lines are easy. So rather than dealing with drawing a curve, what we'll do is, and like stop me if this is getting more than you bargained for, we'll transform the data into a different space, right? We'll play around with it where we're able to draw a line to separate it there instead of something else. So take, for example, are there any markers? No. I'll give you an example afterwards if we have somewhere to draw. Yeah, so we can map it to another one. So like the easiest thing is if you have X and Y, right? So think of kind of the XOR problem. So you have a positive point in at 1, 1 and -1, -1, and then negative points here and here. What you could do is you can actually like multiply X and Y together to get a third feature Z. And then Z is going to kind of put us into a 3-dimensional space now, where 2 of those are raised and the other 2 are beneath the Z plane. And then we could draw a plane to bisect that. So when we get our data, then we'll create that mapping to the 3-dimensional space with Z, and then we'll classify it in that space. That definitely goes beyond the scope of this talk. And what you can even kind of map stuff to infinite dimensional spaces as well. And I don't understand all that, but I like to stay up at night and try to picture it. Go for it.
Here's a controversial question. There was a professor a couple years ago where he talked a lot about brains. Ben talked about deep learning. How closely do you think the perceptron catches?
Oh man, throwing me that one. So I personally don't believe it's a direct mapping, and this is definitely kind of a holy war that you could get in with people. To me, this whole perceptron and deep learning thing, it's a little bit of an analogy. So it's kind of inspired by the biology, but I don't think that it's the way to reproduce in the human brain. Personally, I think it happens to work really, really well on problems for reasons that we don't quite understand, but it's too much of a gross oversimplification of what's going on in here to be the same thing. Mm-hmm. Thanks for listening, and I think Ari's up next. Yeah, I'm excited to hear it.
No, it's here. I just need to find the right one. There it is.
Nice.
Yeah, sorry about that.
Oh, no, sorry. I should have been more clear.
No, last time I saw you, I
I think I
You-
put my
you look
contacts in. I did,
differently, yeah.
haircut. That's all.
but I will get this going for you. All right. You good starting from the beginning?
Yeah.
If you need the screen at all, that screen is on the left screen. So you can just like scroll over and do that. You can see it in the back.
I see.
But yeah, it's just sharing.
Cool. Thanks. All right. How's everybody doing? Good to see you all. So first, I just want to say it's a real privilege to speak for you all. I was surprised to see a Cleveland meetup group for AI, to be honest. And yeah, I'm in the process of learning about it, just trying to figure out what's going on in the great world of AI. Just a little bit about myself. Work for Cleveland Research Company. I'm an analyst there. I cover cloud and software companies like Microsoft and Amazon, and then also helping build out a NLP solution internally. So in terms of why I'm here, what I hope to speak and convey. Last meetup, I saw Jason present some of his findings from a conference he was at, and it just so happened that I was at AI World back in December. So what is AI World? Probably a conference most of you haven't heard of. Very little focus on the algorithms and the development behind AI, more about where is money flowing, who's using it, who's adopting it, what are the actual use cases out there. So this is the second iteration of AI World. About 2,300 people are in attendance. Not that much increase in attendance versus the prior year. Who was there? So you had a bunch of VCs, people looking to invest. You had a bunch of startups. And then you had big tech companies like Google and Facebook with their folks there. And then just general Fortune 500 companies that are working on their development, looking to learn more about what's going on in AI. I noted some heavy participation from the financial industry, but it could be just something I noticed. There was more than 70 presentations there over 3 days. There's a host of things that they talked about. So a lot of panels on chatbots. We'll get into that. A lot of vertically specific tracks, like how is AI being adopted in healthcare? How is it being adopted in financial services industry? And then some more deeper tracks for people that are a little more in the weeds. So there was a track on natural language processing. There's a track on deep learning, reinforcement learning, et cetera. The presenters ranged from folks at the Googles and IBMs of the world to a lot of startup panels where they'd have like 6 startups pitch their AI solution, and then they'd have a panel of VCs kind of judge them and evaluate them on the merit of their solution. So just a little bit more about us, what I do, how do I get to conclusions? We essentially speak with hundreds of people throughout the world to get a sense of what's going on in the industry. You can think of us as, an AI machine or a machine learning model where we ingest lots of insights from people in the industry and then try to spit out an outcome that will predict the future or help people manage their businesses better. So specifically in terms of my background and why I care about AI, in cloud computing, Amazon and Google and Microsoft and IBM are, making, AI tools accessible because cost of computing has reduced it so cheaply. And then, what I do is I speak with end users, data architects. I speak with integrators and consultants throughout the world to get a sense of how adoption is pacing. And we try to come to as unbiased a view as possible as to what's going on in the market and how the different vendors are doing. This is just a snapshot from our company. I just thought I wanted to give you guys a flavor of what we do. And then a disclaimer. thought I'd throw a funny Dilbert cartoon up there. This actually is a very good representation of the state I'm in. We have this AI initiative going on internally with natural language processing. I personally, don't know anything. Like the last talk was brilliant, but way over my head, and you guys are infinitely smarter than I am. And I also have very little, if not no budget to work with. So that being said, talking about where is AI being adopted today, I think this might be helpful for you guys as you're thinking of use cases to maybe you're building out future models. Obviously, I love the the difference between the detergent and the candy, and it's helpful to think of things that could click in our minds and that can connect with everyday people. So I attended about a dozen panels at the conference, and then I spoke with about 20 different individuals across the space. And these are kind of the insights that I came to based on all of that. So first, retail is by far the heaviest adopter of AI today in terms of actual dollars being spent and deployed for what we call, in the industry, there's test budget and then there's running live or running in production. So this is where, production budgets are being spent today. We can go through the list. First, inventory management. I don't know if you guys are too aware, but like Amazon and their distribution centers, they have these Kiva robots that move things around. And also, just going back to the disclaimer, some of the things I might discuss, you may not call AI per se. Like I know like robotics process automation, for instance, is not really AI as you guys might, but industry calls it that. Will just bear with me and forgive me if I classify something as AI that shouldn't be. So inventory management is huge right now. People want their food now. They want to order something on Amazon and get it. And retailers want to ship it to you and make sure it gets to you as fast as possible. So that's one area, one angle. E-commerce, so using like vision learning to say, hey, these are the products that get classified into these groups. When X user, whose data I have, who I see ordered these products in the past and has this demographics, I want to spit up these I think they're most likely to buy these products. And then how do you sort these products intelligently? You're not going to have some guy going through sorting, this is, paint, this is, et cetera. So, training machines to classify and intelligently recommend products for people when they browse. Marketing campaigns, it's really scary. So one of the interesting data points we learned was that after 5 things that you like on Facebook, Facebook can predict within 90% accuracy what your gender is. After 10 likes, they said they know you better than your friends probably do. So it's kind of disturbing in a way how highly targeted the ads are. And yeah, to be honest, there's just a ton of money flowing into marketing and ad campaigns, and then just auto-generating campaigns via email, via message, via banner ads, just literally hundreds of billions of dollars. There's a reason why Facebook and Google are 2 of the most valued companies in the world. The last area in retail, which is huge actually, is customer support. So you think you call into a call center, increasingly, it's not just choose option A if you want to talk to this person, but having a machine be able to understand your voice and be able to intelligently route you to the right place. The retailers we spoke with, even if they're able to cut down a customer interaction by 1 or 2 questions, the ROI is huge because they've got hundreds of thousands of calls a month that are coming through their system. So any way they can kind of use machine learning to narrow that is generating a big ROI for them. Chatbots are kind of an extension of that. Again, just kind of we're hearing a lot of this hybrid approach where chatbot pops up and says, "How can I help you?" and then routes you to the desired location. The last one I thought was interesting. This is kind of new in our research, but we're hearing that Burger King and McDonald's are testing Alexa in the drive-thrus. So coming to a drive-thru near you, you may be ordering your burger from Alexa as opposed to human. And you can only think about the productivity gains that can happen through that, right? Instead of, you know, having somebody, can I take your order, et cetera, you know, big pile up, you just walk in, talk to the person, you know, get through the drive-through, et cetera. Next, finance. So regulation is huge in finance. This whole list I can go down here, but essentially all the transactions that are occurring, all the data that's passing through a bank or an institution, being able to determine is it legal, is it compliant? So instead of having a legion of lawyers or folks reading through documents, analyzing transactions, you develop machines and train them to kind of mirror or replicate the outcomes of these people. Fraud detection is huge, you know, identifying suspicious patterns, detecting anomalies. Again, training models that would kind of replicate what a human would choose and saying, hey, this is, you know, suspicious. Trading I thought was interesting. There are actually companies now that sell software that would intelligently manage your own portfolio, exclusively kind of, you know, machine-based portfolio management, managing your 401k, and then loan approval. So this one's big. Right now, you know, you go into a bank and you say, hey, I have these characteristics. You know, a loan agent approves you for a loan. We're hearing that banks have been rolling out over the last year and a half, solutions based on robotics process automation to kind of assist or in some cases replace loan approval. Moving on, healthcare, big driver. Insurance, we talked about customer support. The other one is claims processing. So, and I know I think we have somebody from insurance company who presented last time, if I'm not mistaken, yes. You can speak to this much better than I can, I'm sure. But, you know, what kind of insurance should I get? You know, there's, you know, again, a whole kind of dichotomy, or not dichotomy, but stochastic kind of tree that goes down, tree of logic to determine that what kind of insurance a person gets, what risk they're at. Again, these companies we're hearing are starting to use machine learning to try to put more intelligence into that process. Diagnosis, IBM Watson is huge in this area with mixed results, I would say. But, you know, using machine learning to analyze drugs, develop drugs, determine if somebody's got a disease. And then last, drug development. I think I haven't heard about it here, but there's, you know, this company that was building drugs overseas using machine learning robots to rapidly test and develop. So what's the future adopters? So we touched on retail, finance, and healthcare. You know, Goldman Sachs, a big bank, kind of gave their vision of where future adoption is going. They viewed logistics, agriculture, and energy as the next industries to take off. You know, you can look through it here, kind of what are the big areas, but self-driving trucks are expected to be a big driver of AI adoption. Energy, smart cities, smart grids, smart buildings, intelligently managing your energy across kind of a whole spectrum is key. So just some considerations for enterprises when building. This is, you know, there's some panels that we attended around this, and then some end users we spoke with as well. But it's really tempting to kind of develop like a generalized AI solution or framework. We've heard that the AI solutions that do the best are very narrowly focused. Yes?
So the AI in Facebook is designed to show you ads after looking at what you post. And so they'd be more apt to sell you an AK-47 to a mass murderer or somebody that how to design it.
Right. So the question was.
They have money from NRA too.
So the question was, how is Facebook using its users' data? Is it used for commercial purposes or, you know, well-being purposes? And yeah, I mean, to be frank, I mean, they sell anonymized data of their users to various agencies. I mean, that's how they're. I can't speak on. I can't speak on behalf. Yeah, I don't know. I don't know specifically if they've got, you know, things that flag sensitive behavior like that. It's a good question. I don't know.
Yeah.
Uh,
So it's marketing.
I know they've worked with the government in the past on, some of, some things in the past around the investigations. They've been somewhat willing to work with the government, but again, I don't have a great answer for that. So in terms of, again, if you're actually, developing an AI application for a company, start with small victories. So don't, have like a firm-wide kind of project you're rolling out, but start in small bits. One of the interesting things we heard was that, kind of like narrowly focused models and data sets work much better than kind of general purpose, models that have very broad use case. Buy versus build, that's a consideration that was brought up in several meetings. It's really tempting to go down the rabbit hole of developing your own algorithms and solutions. But the fact is there are many companies out there already, consultancies and startups that have already built solutions. So, you want to be careful in terms of, what is my competitive advantage in the industry, and how is AI going to help me kind of build on that. And then last is ethics. Maybe it should be first, but implicit bias in your machine learning models. I think the speaker in the last presentation did a great job of highlighting some of the negative ramifications, just our own human biases playing out as we're building models, and unintended consequences as well. One of the interesting things that came up was that unsupervised learning was viewed as kind of in the danger zone, just because from an outside perspective, it's viewed as a black box in terms of how the outcome is being generated. So customers were kind of proposing more hybrid solutions, and I can't explain much more beyond what that means than what they explained. But and then the last one was job displacement. So a big topic was, is AI going to replace jobs? How fast do you want to move the cannibalization of the workforce? And granted, it was an AI World Conference. Obviously, most of the presenters were of the belief that AI is going to be a net job creator. You're just going to see a shift in labor. But I personally believe there's going to be a period of structural unemployment. You could think like the person who's taking your orders at McDonald's now, or somebody who's approving loans. So we're going to have to get reskilled. Myself personally, I feel more and more inept the more of these meetups I come to.
You're smarter than every computer.
Yeah. So, just the state of the industry. What was interesting, I was expecting a more positive spin, it being an AI conference in terms of who's investing and what's going on. But what was really apparent was that there's a lot of investment flowing in, but not too much ROI being generated currently. So the stats were, there's about $10 billion of VC funding into AI startups last year, and that doubled over the previous year. A lot of the panelists were concerned on the bubble in the VC funding space. They said that increasingly you're seeing kind of VC funds going after more and more kind of unproven technologies and startups to invest in, just because the market's kind of so saturated already in terms of who's got funding. So they flagged that valuations are at a peak high, and people are going after riskier startups to invest in. In terms of enterprise spend, so roughly $30 to $40 billion is being spent internally from enterprises on AI development. So the bulk of that is the Googles, the Facebooks, the Amazons of the world. But then you've got, kind of the smaller part of the triangle, companies themselves developing internal AI solutions. This is per Gartner. They're a IT research firm. They said that 4% of enterprises they surveyed claim to have AI running in production. Another 4% are in development, with 50% in testing phase. And then just the last interesting data point, there has been a 4x increase in the mention of AI on Fortune 500 conference calls over the last year. So that brings me to this, the peak of inflated expectations. Gartner posed this question to the audience of more than 2,000 dedicated AI folks. You know, this is what they call, this is a typical tech adoption hype cycle for those of you who are not familiar. So typically a new technology is introduced, and then you see some early adopters, and then people think it's going to take off, and then it kind of hits a wall. And it needs to see that kind of second wave of adoption before it hits mass adoption. So their claim was that AI is kind of at this precipice, and it's unclear if we're going to kind of jump into the mass adoption phase or if there's kind of a few hiccups coming before that happens. So what can we do about that? My takeaway from the conference is that the tech is far outpacing the applications. I was speaking with an end user at Raytheon, and he said, whoever can figure out the UI problem and whoever can create an application will get this right. And MIT had an interesting quote. So they said, this is the editor of their magazine review: "No amount of algorithmic sophistication will overcome a lack of data. Even if you have the algorithms and the data needs to be brought together in the right way. Training algorithms is a resource-intensive effort that may not deliver immediate commercial benefits." So I know this is kind of, again, you guys are brilliant and invest tons of time and mind power into like developing these amazing algorithms and tools and things to solve problems. But at the end of the day, what the takeaway I had is what really matters is the data that you have. Is it proprietary? Is it hard to get to? And then second, is there a clear use case or application? Those are the things that are seeing adoption today. So I guess, how do we bridge the gap? I'm speaking of my own experience. There's a ton of grunt work needed with getting good data. Cleaning, preparing, classifying, it's a lot of work. And there are companies that help with that. But it's just something to keep in mind. Don't assume that there are clean data sets available on Kaggle, or whatever the case is. Data is really hard to come by. The second is work with the business user in mind, work with the end user in mind. It's great if you can figure out how to pummel data through an algorithm and generate an outcome, but at the end of the day, it's a means to an end, right? We need to develop an application that drives a decision. That's what AI does. It helps us make decisions, right? So think with the end user in mind, and then find the use cases. So proprietary data, algorithms, clear application equals a win. So that's all I got. Appreciate you guys bearing with me. I'll open up to any questions. Yes?
That question, you mentioned IBM's watching how tech helps. Could you elaborate on that a little bit?
Yeah, so IBM has been early in terms of developing AI solutions, obviously, with Watson and what they've done. The feedback we've heard is that some hospitals that have rolled out Watson internally, like one example is MD Anderson. They had used Watson to try to detect cancer, and like $20 million was spent on it internally. They fed a lot of proprietary data, and a couple of years after the project, they pulled the plug because it was just losing money, and Watson wasn't proven to be better than a doctor. Some of the folks I speak with, like the system integrators, say that Watson can work, but it's kind of like a 5-year cycle before it starts generating any ROI. There's a lot of training that has to be done. It's not turnkey, and most businesses are on 3-year budgeting cycles at the longest. But that being said, we've heard that those that have waited it out have gotten results. Like one person I spoke with, they work in a project for GSK, GlaxoSmithKline, this European drug company, and they said that they'd rolled out a chatbot based on Watson and had seen an incredible ROI after a couple of months because it was really simplifying the customer support experience. They're cutting down the number of questions by 20 to 30% in a typical customer interaction, which is huge. I mean, they field 100,000 calls a month, 100,000 interactions a month, and to cut that down by 20 to 30% is a big savings. So that's what I mean. Like, what IBM has been pumping a ton of marketing into Watson, to be honest, and kind of hyping it up a lot. And in terms of the areas that we've heard that have actually generated money or ROI, it's kind of few and far between. It's not where IBM would like it to be. It's not where the industry.
But this is based on conversation.
Yes, and our own industry contacts. Yeah. Yes.
In the IT media, why do you think 2018 for AI would be about the CIO finding AI strategy? Do you think that?
So the question was, do I think that 2018 will be about CIOs finding an AI strategy that works? It is definitely top of mind for business users. I don't think they'll find a solution, to be honest. I think again, AI is just a means to an end. It's kind of like been like blockchain too. It's with the rise of Bitcoin, everybody's talking about blockchain and how can I roll out blockchain. I think more test budgets will be flowing into AI. I think more people are looking, but I don't know that you'll see too many more incremental solutions that get rolled out. Yeah.
Do you think you might go to the AI for Good Global Summit up in Switzerland in May?
So he asked about if I'm going to the AI for Good Summit in Switzerland in May, and I don't know. I hadn't heard of that conference, to be honest. Were you at that?
No, I
Okay.
was visiting most.
Okay.
Can't afford all these things.
Yeah. Potentially. Yeah. Yes.
Your last point about find use cases, you write that proprietary data plus algorithm plus applications. Why focus on proprietary data?
Yeah. It's not necessary. From a business perspective, data is viewed as an edge. There's kind of this land grab, like there's for oil, for proprietary data. But it's not necessary. I would say it's most of use cases, it's probably not necessary to have proprietary data. But from a business perspective, like think about Microsoft acquiring LinkedIn. A lot of that was a data grab. So the fact is, eventually algorithms will get commoditized and applications will get commoditized, and all that's left is who has the data, who owns it, who owns the customer relationship. So that's where that's coming from. But I'd say we're so early in this space, like I don't know that it's necessary to have proprietary data. Yeah.
You're defining when basically as a competitive advantage.
Yes, yes. I'm defining this as kind of like a competitive advantage for a business. Yes.
Here's one of your ballpark. How soon will AWS take over?
So the question is, how soon will AWS take over the world? I personally believe it's not so bad to be a fast follower in this market. So Microsoft entered the market 4 years after Amazon did, and really didn't start scaling their business until Satya Nadella took over in 2014. But they've been following very quickly. They've been investing $10 billion a year in their data centers. And like last year, Amazon launched 1,400 new services and features, which was up from 1,000 new services and features launched in 2016. So like people are having trouble keeping up with what came out in 2013. So Microsoft can, and Google for that matter, can kind of see what Amazon comes out with and fine tune it and fix it a little bit. So I personally don't. From the research we do, we see Microsoft likely reaching the same size as AWS in 2 to 3 years. Many businesses are afraid of Amazon because they're pushing into so many industries. They're pushing into retail. Well, so they've killed retail, but now they're pushing into pharmaceutical distribution. They're pushing into media and entertainment. They're pushing into everything. And business users are, wary of working exclusively with Amazon and are looking to diversify away from them. And Microsoft, yeah, they're always going to be 12 months behind where Amazon is in terms of technology in their cloud. But at this point, it's so far ahead. Like, yeah.
You think we'll be doing anything else but those two years?
No, I think
Go back. Yeah, I will. I just.
Oh, wait, do you like cast screen too?
Yeah, I think we
I will once.
Oh, okay. It's up.
You may reach out.
Yeah.
Hello. Yeah, anything.
So his name's already correct.
Cool. Cool. All right, one sec. Microphone's here? Maybe. Go like 15. Oh, it's 15. No, it's time. Yeah. Okay.
All right, guys, we're gonna get started again. So this last talk is about OpenMind, which is a project that Bobby and I are working on with a lot of other people, like all around the world. It's a really exciting project. He's going to talk all about it, and I hope you guys really enjoy it. And there will be, so yeah, I guess you'll talk about that.
Yeah.
Okay.
Yeah.
Yeah, then we're just going to get started. And this is Bobby.
Okay. Hi, as Jason said, I'm Bobby. I'm a student here at Case. I also contribute to OpenMind. So OpenMind is, OpenMind is a community focused on building open source technologies for the decentralized ownership of data and intelligence. So Ari actually gave a great setup to this talk, which we'll see shortly. So the key activities OpenMind undertakes are raising awareness for the necessity of private machine learning. We also build tools to lower the barrier of entry into private machine learning. And we have some fun. This is photos from our last hackathon, which took place in 29 cities across the globe. If you can see on the bottom right, it even took place in the snow. So an overview of what we're going to talk about today. We're going to talk about why the common AI business model has privacy problems, and then how OpenMind intends to remedy those problems through the use of federated learning, multi-party computation, and gradient marketplaces. And then finally, we're going to give you a roadmap for how we intend to proceed in the future. All right. So let's say we're going to start an AI company. As I already said, first you need some data, and algorithm. All right. The way you typically get that data is you create something like a social app, a la Facebook, and you acquire that data about people. Then you have that data, you use it to train a model, which can take data that people release as public and use it to predict data that people find as private, like in the loan example from earlier. Like you take people's attributes and then you predict their credit score. And then finally, once you have that model, you sell it to somebody or use it in-house. So with our credit score example, the big banks use it to see whether to give somebody a loan. So to reiterate, the steps are acquire data, train a model on that data to predict unknown facts from known facts, and then finally sell the use of that model. There's a few problems with this. With acquiring the data, people lose control of their data. And because people lose control of their data, they're unwilling to give up some sensitive data, such as genomic data, which means that you can't make products that predict on those factors. Additionally, when you're training the model, people who don't want to give up their privacy lose their privacy by virtue of other people giving up their privacy. So if, say, I give up my information that I find is private, they can then train a model on that data that will predict your information. Additionally, because these data sets are private, there's lack of competition in these marketplaces that solely hinges on your ability to collect this data. And then finally, depending on how you collect the data, there can be large bias in the data sets depending on who's willing to opt in. Finally, selling the use of the model causes people who own the data to use the natural source of income that is their data and gives it to the company that trained the model. Additionally, it makes it hard to predict the value of data and the accuracy of the predictions because the data is so hidden away. And then finally, it's hard to protect these models, which lead to them getting out. So the question comes, how do we solve these problems? So the initial solution that we have for this is to train AI on data we can't see. It's hard for people to lose control of their data if the company that's training the model never sees it in the first place. This is a privacy win. All right. So now we're going into the how for doing this. And first, we're going to talk about federated learning. Federated learning's a big topic nowadays that sounds a lot more complicated than it is. So in an unfederated sense, one company collects the model, the data, and trains it all under their roof. With federated learning, each of the people keep control of their own data, and the company keeps the model. They then send the model to one of the people who trains the model on their data, and then sends back the updated model. This process then repeats across all the different users until finally you end up with an optimized model, just like if you trained it with all the data under your roof to begin with. This allows us to train on data we can't see, which is a win. However, it creates additional problems. While the data is private, the AI isn't kept private, and these models can be very valuable. Like Ari said earlier, it's a $50 billion business. And then because of how the gradients are distributed, they also reveal information about the data. And you still can't train sensitive products. So you want to train AI on data that we can't see while also not giving away the model. This brings us to the next two topics, which are homomorphic encryption and multi-party computation. I'm going to skip over homomorphic encryption because it's shown to not be computationally feasible for this project, but wanted to mention it so that people didn't have that question. So multi-party computation operates on a fairly simple principle. Say we want to add two numbers together. Say we want to add the numbers 5 and 3. The sum of those numbers is 8. However, if we split up the number 5 into 5 other numbers, which all add up to 5, we can then also split up the number 3 to 5 numbers which add up to 5. And then if we add each of those individual shares together, we can get the final product of 8. Now, this generalizes to more complicated equations. And like Billy showed earlier, training neural networks is just adding and multiplying. So this allows us to compute functions on our data without actually seeing the model. So we split the data into public and private shares. The user keeps control of their private share and sends the public share to the data trainer, or sorry, the model owner. And then the model is also split into public and private shares, in which the public share is sent to the data owner who already shared their data. Because of multi-party computation, this means we can train the model. So because of this, we've shown that we can train AI on data we can't see while also not revealing the AI. We also want a way to price this data so that people can be adequately compensated for their data. The way we go about this is we see how their data updated the model compared to where the final model is and estimate the distance between the two of them. Now we're going to talk about gradient marketplaces. Gradient marketplaces are how this works in practice. The people who own data set up essentially a worker on this network which holds onto their data and also does processing. This worker trains and then additionally validates the model so that they can be compensated. So we've shown, sorry about that. We've shown why we want to do this and how we plan on doing this. So now we're going to talk about future steps. Sorry, this is a status update first. Last January, we had a hackathon in 29 cities, one of which was Cleveland, in which there were 400 people online and 70 people who showed up to the individual events. This number is actually out of date now. There's over 2,200 people in our Slack channel, of which 130 of them have contributed to the code base. And recently, we were able to train a model that was created in the UK on someone's computer in Canada in a total of 15 seconds. Additionally, we've created interfaces which mimic common deep learning frameworks so that there's less less learning for adoption. And then finally, we've started working with Unity's ML agents team to bring reinforcement learning into this platform. So we also have a hackathon tomorrow in 22 cities, including Cleveland. There's a meetup event in this meetup that if you're interested, you can sign up for. It's all weekend long. You can come whenever you'd like. If you're interested in learning more, our Slack channel is there. And then our planned milestones for the meetup, are speeding up our training grid, making the multiplayer or multi-party computation more robust, and creating our first implementation of federated learning. All right. So with that, oh, yes, I forgot about this slide. So this is a roadmap for our project. Currently, we're working on deep learning in Unity, as well as a decentralized model training grid. And we plan to move into public federated learning and private federated learning. So, yes.
Multi-party.
So if I'll go back to the slide to four slides. All right. So the multi-party here refers to when we split it up into 5 shares, we distribute each of those shares to different people. So those are the different parties, and then they do their own computation, which is then combined to get the final result. Yeah. All right. Sorry, I kind of rushed through this. So the way this works is, say I have the number 5. I can pretty easily generate 4 random numbers, which I then subtract from 5 to get a set of 5 new numbers that add up to 5. Additionally, say you have the number 3, you can also create 5 numbers which add up to 3. Then we each send those data to 4 other people, 3 other people. I send one of my shares to you, you send one of your shares to me. And together, everyone ends up with 2 numbers, one of which was a part of the original 5, and one which was a part of the original 3. We then add up those numbers to get some number. This number has no meaning. But when we add all of those numbers back together, we get the result without any of us learning anything about the original numbers.
How does an update step happen? So how does that apply? Where will the update, like the model training update happen? So where does that happen?
This is a fairly simple example for how multi-party computation works. When you get into multiplication, the math gets a lot uglier, so we weren't showing it here. The way the update step would work is you can explicitly compute a function for the update step given the data and the current weights, which would just be a functions of addition, multiplication, and explanation, which you can then evaluate. These steps can be chained together, so you evaluate that function, which the resulting output is the update. Yes?
You need a central node.
You don't. Unfortunately, we don't have a demo here today because some changes were pushed to the code base, which broke our demo with not enough time to fix it. But in previous instances when we trained it, there were no central nodes. Yes?
So this seems like it would work with an example as simple as integer addition, but is this even feasible for something a little more complicated or a lot more complicated, like you mentioned genomic data or something earlier?
Yeah.
You can't exactly anonymize, mix up DNA sequences because that will give you a completely incorrect output, right?
So,
so anything more complicated would this even be feasible?
So the way most models work is just doing math on the input. So you represent the DNA sequence as like a series of numbers from like 1 to 4. Messing up the input is undone at the end. So the computations that each of the workers do is designed so that when they're combined together at the end, all of the messing up is undone. So to answer your question, yes, it generalizes.
And there are theoretical guarantees on like this working for like chaining together these operations in the way that it would be chained together in a perceptron or a neural network or something like that. And there are also theoretical guarantees on the amount of privacy you get depending on how many people are taking place in the computation. And also, it's like dependent, like they phrase it in the sense of like assuming that half the people here are actually secretly collaborating and trying to get the data like undiscovered, can the data still be hidden during this computation? And that's actually what Bobby's working on mostly.
Yeah.
So if you're interested in that,
If you have more.
The risk of oversimplification, it sounds like
It is.
yes.
It's a form of encryption.
The main like thing that we're adding is we're trying to build a decentralized network where people can do this, and so the data never has to be siloed anywhere, right? If everyone's on the same network, they can all communicate with each other and partake in these computations. And we're building a client that can direct all that. So a data scientist can just spin up this client, plug their model in, and specify the data they want, and then push that job to this network. And then people who are also on the network who have the data, they can see if they fit the job, and then they can choose to accept it or not. And then they'll go, and whoever's partaking in the job, they will collectively engage in multi-party computation to train the neural network. And that's generally how you train these networks in a way that the data and the AI are all kept safe using the system.
It's a lot of hands. I guess we'll just go that way.
Does this model apply to algorithms that aren't necessarily
Currently, so if you're asking about like logistic regression or such, or
what big decision?
okay, no, not easily, theoretically. I believe you were next. Yeah.
At one point you mentioned something for 15 seconds. I have no that.
So
it was an XOR model, though, right? So
yeah, it was a fairly simple model, but regardless, that model traveled from England to Canada, was trained, and then traveled back in 15 seconds. The reason that time is relevant is it's not minutes long, it's seconds long. So the person training the model probably wouldn't care.
If you had a really complicated model of training, what's the penalty?
Negligible. All right. I think you had a question.
How many other nodes does it give?
So it depends on the level of privacy you want. Currently with this system, at least 2. With other ones, you only need to know the person who has the data. We're currently moving towards the latter one. All right, Billy?
I had an easy one. One of those questions sparked one that was a little more technical. So we'll start with that one, and then we'll do the easy one second. So you said that the amount of time that the training has is negligible, right?
Mm-hmm.
Maybe this is like me taking the oversimplification too far up to the actual thing. But in here, right, instead of just doing 3 plus 5, I'm doing that addition 5 times. So it seems to me like it should take 5 times as long, plus a little bit extra.
So each of these steps happen in parallel.
Right.
Yeah.
So the total like CPU time.
The total CPU time goes up, but the total real-world time does not.
Oh,
Other than the sending.
The combination of everything? But that's negligible.
Negligible.
And then the low ball, what's your stack look like? Just a quick overview. And what do I need to know to come to the hackathons?
So in order to come to the hackathon, you need to know how to open a text editor. As far as what the stack looks like, there's currently a couple stacks that are going on in parallel. The main one, which is used with the multi-computation, is built on top of NumPy. And then communication is done through the interplanetary file server system. It's basically a fancy way of saying it's a distributed pub sub. And then on top of that is a Keras-like interface.
That's for grid.
Actually, one just uses actual Keras.
But then there's also Python.
Okay, and then the other one actually, instead of having Python or having NumPy as a backend, actually uses Unity, which means you can run it on your Xbox. Yes.
I'm having trouble envisioning the world. Do you have something?
Yeah. So, like, let's say you have data that you would never want anyone to know about. Right? We all have data like that, and in some cases, people have designed systems to figure it out from browsing activity or whatever. But there are also even more secretive pieces of data that we don't even put on the internet at all. Except maybe Google might know through our search history. But for example, like if I go to a therapist and I speak with a therapist and they take notes, psychotherapy notes, those are incredibly sensitive, and no one would ever in their right mind like put those in the hands of a corporation to learn from, right? So we have models that we can't train because the data is so sensitive that it doesn't make it to like production systems or even to the prototyping phase of really training models. So the hope is that if we can keep the data secretive, people will be willing to share it, because if we can provide theoretical guarantees as to no one ever seeing that data, it's always on your computer, it never leaves your computer, then perhaps we'll be able to open up a new class of models that can't be trained with the way the current AI business model is.
So the business model would be paid.
Yes,
Yes.
the data scientist would offer up a bounty.
Mm-hmm. So this was what we were getting at with the gradient marketplaces. So when this training is undergone, the model owner pays the data owner like a little bit of money for the use of their data. And then depending on what data they're using and how much computation is required on the data owner's side, they could either refuse or accept that payment.
So it's not something that's going to replace looking life or something, more like getting data.
Ideally, we'd also like to incorporate the clicking like data into this so that that data doesn't have to go out to, let's say, Facebook, for example. But currently, that's not the case.
Yeah, Facebook will likely collect that data no matter what we do. What we want to do is have adapters where you can download your Facebook data, post it on your computer, and other companies who aren't Facebook can use your Facebook without ever seeing the data. So, I mean, we can't fix that Facebook is collecting all our data, but what we can do is allow other people to compete with Facebook based on data.
And then compensate the people actually creating that
still
data.
be compensated.
Yeah, like that individual data would be just information coming off of someone's Fitbit or something.
Yeah, that's
Yeah.
another one. Another good one is genetic data.
Mhm. Yeah.
So that's something that's stored in a centralized location, though. It's not like the user has access to their
Genetic?
data.
Well, no. So if you like work with Ancestry.com or
Do they give you access to your?
yeah,
They
send
give you your genome.
Yeah, they send you like the whole thing, and then you have those files on. Do it. You can then upload those to like OpenSnip actually, or like you can host them online for free, but like it's all public.
Yeah.
So the idea would be that you can do that without
Actually giving your genome.
That's it.
Yeah.
You send the full model, or you send a portion of the model, right? It's like a
Yes.
representation of the model, but it's the simple size of the model.
Currently, yes.
And is like, in terms of the theory behind this, that's something that can be used.
Maybe that's not something we've looked into yet.
I don't know.
Well, I mean, depends on what your system you're working from, but the only way to get data from you is that you have a user iteration of a pretty big model, and maybe that's depending on the size of the model that you're working with. That might be a cost in itself. So, or you might not even be able to do it like that.
Yeah, so it likely wouldn't be done on a phone. I don't think we're like that's gonna
Currently, currently it's not planned to work on phones. Eventually, as phones evolve, they would be able to run it. And then it's up to the data owner to decide whether or not to accept the model to train.
Actually, today they came out with News.com, who's a company that designs flight processing systems. They're like 20 hours. What processes designed specifically on AI that they're going to be like selling to some So eventually, the hardware is going to be on the phone, but we might get there. It's going to take.
Okay. So, Caig, I saw you. Yeah. So using the NumPy side of things vary. Using the Unity side of things also vary. So, yeah. So this is something we've actually talked about a lot. Yeah, typically the model trainer, like the person who wanted to create the model would construct their own validation set. Yes, but that's still a lot less data than you have to acquire a full training set. That is something we're working out on the theoretical side as well.
Yeah, that's actually like we just had a meeting to speak about that where like I think we got like a pretty good idea of how we're going to measure contribution of each person, and that, it turns out if you look through the literature, like people haven't really looked into that much, and so like we're gonna do it and see how it works.
Mm-hmm. It depends on the scheme you're using. On the one we're currently using, yes. On the one we're moving to, no. The one that's currently implemented was a very naive proof of concept. What's the actual name for that? Sorry, I'm trying to remember the name for a specific term. That's the name of the no. They a couple more communications is the major difference.
What do you mean by that?
Like you have to send a few things back and forth more. Additionally, a scheme we're looking to moving towards more down the road requires actually less communication, but it's more like it requires more computation. It's kind of a trade-off.
What's the name of the second one?
The one we're going to towards first is called SPDZ, and then finally we're moving towards government circuits. The point of this talk wasn't really about the crypto schemes, so I'm going to save that for after.
How many of this 10 on the scheme? How many of this 10 that
Depending on the scheme, anywhere from 5 to 10. The one we're doing currently, you need 5. The one we're moving to, you need 10. So as long as the data owner is one of that 10, you're probably good. So the we I'm referring to is the Open Mind group. It, like mentioned earlier, it's about 2,000 people scattered across the globe.
Although, like, people who are really active in it are probably like a couple hundred.
Yeah. You and then, yeah. Okay. So the goal for people hosting the nodes is everyone. So you have data, I assume, that you'd like to be compensated for. So if, as a background process on one of your devices, you have this worker running that every so often just gives you money because your data trained a model. As far as the people wanting to train models, we predict it to be similar people to who are already starting AI startups or just established companies. Right. They could do that as well. One use case that we're looking at down the road is partnering with hospitals to gain access to their large swaths of data to train models across hospitals, across country lines. That is a good one. Yeah, thanks. So the payment section is still in flux. Initially, it was on the Ethereum blockchain, so you'd be paid in cryptocurrencies. But that's something we're looking into because the blockchain is very slow.
And the blockchain, well, no. Like the payment scheme, I think is still planning to be on a blockchain, but the currency, they don't want to tie it to a specific cryptocurrency because it's actually volatile, right? There's no like really stable cryptocurrency. So like, we'll see how it goes.
Why is there payment involved in this at all? I mean, I understand that down the road, like some company wants to set up using this open source software that can be developed by a community of people across the globe. Why are you guys even talking about pricing this? In terms of building
the pricing doesn't go to us at all.
No, I know. What it does is someone has to pay the user.
So the user, the reason we wanted to build in pricing to this project is we feel that people who own data should be compensated for the use of their data, which is why that's a conversation.
And like it wouldn't. I mean, I think I'm not exactly sure how blockchain works, but I think there's some like third party that has a stake in, like putting up the cash or something. But there has to be someone involved in that transaction. And they said we're doing it. So like once it clears like the blockchain and like then the parties get like compensated. And
There's an inherent value with this idea of like, especially for earlier projects like healthcare and the nonprofit perhaps, there's just inherent value of people just getting more data. So like SETI or all these things, as long as I know that my data is secure, I might be much more willing to do that. So like I don't know.
So we're planning on also offering that as an option. Like
yeah,
theoretically, you don't have to offer currency, but people also don't have to train your model. It's up to the user.
well, it's probably going to be like different channels. You go on like the marketplace, you can go on like the open source.
So there's going to be like a central repository of like things that people are going to post saying, I want this to X data that you have. So that,
not
and this is what we're offering.
Not centralized. It'd be decentralized. So using publisher and subscriber services, you're able to, and distributed publisher subscriber services, you're able to send out this message to everybody who's listening to this channel, who can then decide if they want to train your model. Yes. Exactly.
Well, and they could potentially get paid for it if not generated. So that's I think that's what we're banking on as far as like adoption picking up, right? I mean, there's a lot of people, everyone out there has data. Anyone uses a device generates lots of data, and especially people who don't make much money, like that money that's going to come from using the data and training is going to be a larger portion of their income in general. So I mean, like, I'm not saying we're going to solve wealth inequality, but
Yeah, it depends on how much. We plan on guaranteeing that they will never see the raw data. Can you learn things from data? Yes. However, you also have to be willing to offer up that data for them to run the model on. What we're primarily interested here is training the models, but the actual information they gain about you is when the model is run.
there are also a lot of like interesting questions about like how do you ensure that people are using real data and not fake data. Yeah, right. So like fake data, you can just put in random noise and it's potentially fake data, but then that random noise won't generate, it won't contribute to the model's final performance. So if you have a way to evaluate how each person is contributing to that performance, then you solve that. But then you can also build a generative model that actually creates data that does help the model. And maybe you should be compensated for doing that, because that's also labor that, like you're contributing to the product. I don't know, there's a lot of questions around it that we haven't solved.
There was actually there was also a speaker about
All right. Thank you, everyone. I'm lost.
Take care.